How does transistor biasing work for signal amplification? Imagine trying to turn up the volume on a tiny speaker so it fills a room without distortion. That's what transistor biasing helps achieve in electronic circuits. When you want a transistor to amplify signals, you need to set it up just right. This setup is called biasing. It involves applying a steady direct current or voltage to the transistor's terminals to create a stable operating point, often called the quiescent point. This point is like the baseline or starting position that keeps the transistor ready to amplify signals smoothly. In a bipolar junction transistor, which is a common type used in analog signal processing, there are two main junctions to consider: the base emitter junction and the collector base junction. To get proper amplification, the base emitter junction must be forward biased. That means the voltage at the base has to be a little higher than at the emitter, allowing current to flow into the base. The collector base junction, on the other hand, needs to be reverse biased. This means the collector voltage should be higher than the base voltage, preventing current from flowing there unless controlled by the base current. By carefully choosing the right resistor values and voltages, the biasing circuit sets the collector current, which is the output current, based on a small input current at the base. This small current is the input signal that you want to amplify. The biasing ensures that even when the input signal varies, the transistor stays in its active region. This is the region where it can linearly amplify the input without clipping or distortion. If the bias is too low, the transistor might turn off during part of the cycle, causing distortion. If it's too high, it can go into saturation, which also distorts the output. There are different ways to bias a transistor. Fixed bias uses a set voltage applied directly to the base. Voltage divider bias uses two resistors to create a stable voltage at the base, making it less sensitive to temperature changes. Emitter feedback bias adds a resistor in the emitter leg, providing negative feedback. This helps keep the operating point steady even if the temperature or transistor parameters change. Practical circuits, the input AC signal is added on top of the DC bias voltage at the base. The transistor then acts like a controlled switch, turning the small input current into a larger collector current. This larger current causes a bigger voltage change across a load resistor in the collector circuit, producing a larger output signal. This process faithfully reproduces the original waveform but at a higher amplitude, which is the essence of signal amplification. To sum up, transistor biasing works by establishing a stable DC operating point through proper biasing of the junctions. It keeps the transistor in its linear active region during signal variations. This allows a tiny input current at the base to control a much larger current at the collector, resulting in effective and reliable signal amplification. Techniques like emitter degeneration help improve stability and reduce distortion, making the amplifier more dependable in signal processing and control systems.